Okay, let's do the next one. If x bar and y bar are sample means comprised of n IID random variables arising from distributions having means mu x and mu y, respectively, and a common variance of sigma squared, what's the variance of x bar minus y bar? Okay, this seems like a very confusing problem, but let's talk our way through it because it's a quite important problem. So let's orient ourselves because this is important for us to think about. If I have a density that has mean mu x and it has variance, the sort of spread of it is governed by sigma squared. That's a population distribution. That's assuming that if I draw data from this population, that their probabilities, the probability they take various values, will be governed by this general law, this general density distribution that is sort of a conceptual component of a population. Maybe if we were to collect an infinite amount of data, we would know this density exactly. If I were to draw n observations from this density and take their mean, I get another random variable, and that's a single draw from another density. One that's the density of the average of n draws from this existing density. And we know a lot of things about that density. For example, that it is centered at the same place, but it's shrunken in. It's compressed around mu x a little bit more, and that's just saying that x bar is a good estimator of mu. It's a better estimator of mu than just a random observation from the original population. The average of n observations from the original population is a better estimator because the density governing the probabilities associated with x bar is more shrunken around the thing that you're trying to estimate. And in fact, we know how to relate the variance of this density, the density of the x bar, to the variance of the population. The variance of the original population is sigma squared, then the variance of x bar is equal to sigma squared over n. So the result of collecting n observations and taking a mean is to get a new random variable, the sample mean, whose variance is now shrunken by a factor of n, which is a good thing, right? And it's also centered around what you want. The density is centered around what you'd like to estimate. And similarly, the variance of y bar is going to be sigma squared over n because we assume that the population that the y's were drawn from had the same variance as the population that the x's were drawn from. Okay, so now let's talk about the variance of x bar minus y bar. Well, so we said that the data were independent, that the x's were independent of the y's, which is good because that means that our variance adds. And so we could write variance of x bar and then variance of y bar. And you'd be inclined to put a minus sign here, but that would not be right. And it's a plus sign. And the reason is because think about it this way. If I were to do variance of x bar plus negative y bar, and my x bar and y bar are independent, then that would be the variance of x bar plus the variance of negative y bar. And then if I were to pull out my -1, it gets squared, right? Remember that rule, if we pull something out of a variance, it gets squared, and then the square of a -1 would be positive. And so at any rate, the long and short is if you subtract two things, their variance still adds. Now, if the two things aren't independent, then we may have other stuff over here that we have to add in. Subtract off, in fact, in this case. But these things are independent, so there is no covariance term or other thing we have to subtract off. Okay, so let's plug in. We have sigma squared over n for x bar, sigma squared over n for y bar for the variance of y bar, and they add, so it's equal to 2 sigma squared over n. And so let's go back and try that as an answer. 2 sigma squared over n, submit answer. All right.